Hello, welcome to this session on the continuation for the rectangular waveguide. In this session, we are going to discuss the power loss on the waveguide walls and the attenuation as a result of power loss, the expression for the attenuation. So, first of all, we consider the attenuation of an electromagnetic wave in a homogeneous medium. So, we know that the propagation constant is given by root of minus z cap y cap, where z cap is j omega mu and y cap is sigma plus j omega epsilon for a medium with finite conductivity. So, we also know that in general the complex propagation constant is given by the addition of the real and the imaginary parts of the propagation constants, which are given by k prime for the real part of the propagation constant and minus j k double prime for the imaginary part of the propagation constant. So, this minus sign is dictated by the fact that the electromagnetic wave will experience attenuation and not get amplified as it traverses through the medium. So, that means e to the power minus j k z should be e to the power minus j k prime minus j k double prime z, and that is e to the power minus j and that is equal to e to the power minus j k prime z e to the power minus k double prime z. So, a good conductor is characterized by sigma is very much greater than omega epsilon. It is characterized by the fact that sigma is very much greater than omega epsilon. So, under that condition for a good conductor, we have k is equal to root of minus j omega mu sigma plus j omega epsilon which can be approximated as root of minus j omega mu sigma, retaining only the first term because sigma is very much greater than omega epsilon, and that can be broken up into root of minus j root of omega mu sigma. Now, minus j can be written as e to the power minus j pi by 2, and therefore, k or the complex propagation constant can be written as e to the power minus j pi by 4 root of omega mu sigma and that can be broken up into 1 by root 2 minus j by root 2 root of omega mu sigma, that is root of omega mu sigma by 2 minus j root of omega mu sigma by 2, and as a result k prime or the real part of the propagation constant becomes root of omega mu sigma by 2, and the imaginary part of the propagation constant becomes root of omega mu sigma by 2 as well. So, let us call this equation 55. Now, we know that the skin depth is the depth for which the field amplitude becomes 1 by E times its initial value or 36.8% of its initial value. So, that is corresponding to the condition k double prime delta as 1, that is corresponding to the condition k double prime delta is 1, and as such delta is equal to 1 by k double prime, that is root of 2 by omega mu sigma. So, that is 56. Okay. So, the density of power flow into the conductor, which is ultimately converted to heat, is given by S equal to E cross H star where the ratio between E and H is given by eta m, which is the surface impedance of the metal. So, E becomes equal to eta m h and S becomes equal to eta m h cross H star, that is eta m mod H square u z. So, let us call this equation 57. So, let us call this equation 57, where H is the magnetic field at the surface. So, the time average power dissipation per unit area of cross section, which is given by P d tilde, is real part of S, that is real part of eta m mod H square u z, that is mod H square r u z watts per meter square. Let us call this 58, where R is real part of eta m So, this being called the intrinsic resistance or the surface resistance of the metal. So, now let us consider the T01 mode of the waveguide and find out the power dissipated per unit length in the wall. So, let us consider the wall at y equal to 0 and let us consider A01 to be the RMS amplitude of the psi function. For the T01 mode. So, we call the power dissipated per unit length as PD1 tilde, the time average power dissipated per unit length, that is given by PD tilde y equal to 0, because we are interested in the power dissipated per unit length on the surface y equal to 0. Now, on the surface y equal to 0, that is the two narrow walls of the waveguide, the tangential magnetic field is Hz only for the T01 mode, and therefore, the PD1 tilde expression becomes 0 to A 0 to 1, because only Hz is present. So, it will be Hz square dz dx. Now, we know that Hz at y equal to 0 is given by A01 by j omega mu. We can obtain it from the previous expressions for the expressions of the Tmn mode of the waveguide, k square minus kz 01 square cos pi y cos pi y by b e to the power minus j k z 01 z at y equal to 0, and therefore, getting rid of the cos term or substituting y equal to 0 here, we get a 01 by j omega mu k square minus k z 01 square e to the power minus j k z 01 z. And therefore, the expression for P d 1 tilde becomes equal to R 0 to A 0 to 1 A 0 1 square by omega square mu square k square minus k z 0 1 square whole square d z dx. And when we perform this integration, it becomes A r A 0 1 square by omega square mu square k square minus k z 0 1 square whole square. And since k square is k z 0 1 square plus pi by b whole square, that is omega square mu epsilon, we have the expression for P d 1 tilde given by A r A 0 1 square by omega square mu square pi by b to the power 4. So, you can call this expression 59. And an equal amount of power will be dissipated at y equal to b. An equal amount of power is dissipated at y equal to b. Then we next go to the power dissipated at the wall x equal to 0. So, at the wall x equal to 0, we have two tangential components of the magnetic field for the T 01 mode. One is H y and another is H z. So, therefore, P d 2 tilde, which is given by P d tilde at x equal to 0, that will be given by r 0 to 1, then 0 to b, mod h y square plus mod h z square dy dz h y at x equal to 0 will be given by a 0 1 k z 0 1 by omega mu pi by b sin pi y by b e to the power minus j k z 0 1 z. Therefore, mod h y at x equal to 0 will be everything other than the e to the power minus j k z 0 1 z term, because its modulus is 1. So, a 0 1 kz01 by omega mu pi by b sin pi y by b. Similarly, mod h z at x equal to 0 will be a z 01 by omega mu k square minus k z 01 square cos pi y by b, and therefore, from the expressions of h y and h z, p d 2 tilde becomes finally equal to r a 01 square 0 to 1 0 to b, because we are going a unit length along the z axis, becomes k z 01 pi by omega mu b whole square sin square pi y by b plus 1 by omega square mu square k square minus k z 01 square whole square cos square pi y by b cos square pi y by b dy dz. And then using the form and then using the expression k square equal to k z 01 square plus pi by b whole square equal to omega square mu epsilon the expression for P d 2 finally turns out to be, you can just verify this, r a 01 square pi square epsilon by 2 mu b. And like before, an equal amount of power will be dissipated at x equal to a. So, the total power dissipated at the 4 walls of the waveguide dissipated per unit length at the 4 walls of the guide becomes equal to P d 0 tilde, and that is equal to 2 P d 1 tilde plus P d 2 tilde. So, let us call this 61. Now, considering the waveguide as a transmission line, we can consider the voltage variation along that line to be of the form V equal to V 0 e to the power minus alpha plus j beta z, because there is attenuation along the guide due to the power loss in the 4 walls of the guide. This attenuation is being accounted for by this term alpha. Similarly, the current is given by V by Z 0. So, therefore, the power flow is given by V I star and substituting from I star from here, I star becomes equal to V star by Z 0 star, that is V 0 star e to the power minus alpha z e to the power j beta z by Z 0 star. Note the change in sign of e to the power j beta z. So, therefore, my P f becomes equal to V I star, that is equal to V 0 e to the power minus alpha z e to the power minus j beta z V 0 star e to the power minus alpha z e to the power plus j beta z divided by Z 0 star, and which ultimately evaluates out to be mod V 0 square e to the power minus 2 alpha z, because this term and this term cancels out, divided by Z 0 star. And that is P 0 e to the power minus twice alpha z. So, therefore, the time average power flow which is P f tilde equal to real part of P f, that is real part of P 0 e to the power minus twice alpha z. So, this is 62. So, then P d 0 tilde which is the time average power dissipated per unit length, becomes equal to minus d p f tilde dz, and that is equal to minus of minus twice alpha real part of p 0 e to the power minus twice alpha z, and that is twice alpha, and that is twice alpha real part of p 0 e to the power minus twice alpha z. So, let us call that 63. Okay. So, therefore, the attenuation constant alpha can be written as P d tilde divided by twice P f tilde. That is using 62 and 63. So, therefore, that attenuation, and therefore, the attenuation due to the conductor loss in the 4 walls written as alpha c is twice P d 1 tilde plus P d 2 tilde, which is the total power dissipated in the 4 walls per unit length divided by 2 P f tilde. So, P f tilde can be substituted from expression 54, which we have already evaluated. With m equal to 0 and n equal to 1. Corresponding to the T 01 mode. So, this is using 61, you can call this expression 65. So, this expression evaluates the attenuation constant due to the power dissipation at the 4 walls of the rectangular waveguide. Okay. This concludes this section. We will stop here at this point. Thank you.